we're given a question where we're asked to calculate the energy transfer after 1 hour in a wall section measuring 2 meters by 1 meter by 0.04 meters thick with a thermal conductivity of 0.1. And then it says the opposing sides of the wall section have a temperature of 15 degrees Celsius and 10 degrees Celsius. So it's a pretty straightforward question. It's just asking for the energy transfer, which is just Q. And before we solve for it, let's go ahead and draw a picture of what it's talking about. So I'm going to start by drawing the thickness of our wall. So just a simple rectangle. So this will be the front or the thickness. We'll draw it at an angle. And then back here, we'll draw the back of it. It's not going to go down quite as far in the back. But hopefully by now you can kind of see how this is working. I'm going to connect the bottom, and I'll connect the top two corners here. And hopefully you can see this is our wall section. So here would be its thickness from left to right would be just 0.04 meters. And then the length of the base would just be from the front to the back. We'll say that is 2 meters. And then, of course, we can add the height, which is just 1 meter. And we'll draw the top and the bottom here connected. And so here's our wall. And on one end of the wall, it says it's 15 degrees Celsius. And on the other end of the wall, it says it's 10 degrees Celsius. And we'll draw the hotter side as red and the colder side as blue. And of course, this wall has some thermal conductivity, or K, and actually, let's pick a better color, but some thermal conductivity, which we'll call K, of 0.10. So what's going on here? Well, if we look, it's hotter on one side of the wall than the other, so the energy from that side wants to go through our wall to the other side. The heat on one side wants to be transferred to the heat on the other side. And we call that heat transfer Q. And the question is, what is Q? What is our energy transfer? And you might think, well, can we use our formula from before of mass times specific heat capacity times the change in temperature? But if you look, we're never given the mass of our wall, or we're never given the specific heat capacity of the wall because we don't know the material. So how could we know the specific heat capacity? And so we don't actually have enough information to use this formula. But if you look back in your notes, we're given a formula. Another formula with Q in it. So we can solve for Q using these values. So we can go ahead and write out that equation for ourselves. Let's say power equals energy over time, which we knew. We knew this formula. We've used it a few times before, but we can go ahead and convert this by multiplying by time on both sides, and we get Q equals power times time. So we have another formula with Q in it, so we might be able to solve for energy transfer using that formula. And we're given a lot of information in this question. Let's see if anywhere in that information we're given the information we need to use this formula to solve for Q. So the first thing they give us is time. And if you look, that our time is written delta little t, so delta little t equals 1 hour. Okay, and let's go ahead and convert that to minutes. So there's 60 minutes in an hour. And then we can go ahead and convert that to seconds, saying there's 60 seconds in every minute. So if it's 60 seconds per minute, 60 minutes, that's 60 times 60 is 3,600 seconds. And so that's the change in time. Then we're also given a length, a width, and a thickness of a material. So we can go ahead and say, well, thickness is L. So we can go ahead and say L equals 0.04 meters. That was pretty easy. And what about this 2 by 1? Well, if you look, that's what we're going to use to find our area. So our area, our formula for area of some structure is base times height. And of course, our base, the length of our base is 2 meters of our wall. And we're going to multiply that by our height of our wall, which is 1 meter. And what do we get? Well, we get 2 meters squared. And then we're also giving a thermal conductivity, which is K, of 0.1, so we can say K equals 0.10. And we'll go ahead and leave the units out of this. You can actually calculate the units if you want to use this formula over here, but we're not going to worry about it. I'm not going to confuse you with the units right now. And then lastly, we're given the final temperature and the beginning temperature, the temperature on one side and the other. So we're given the change in temperature, which we can say is 15 degrees minus our 10 degrees. And I guess I should say Celsius and 15 degrees Celsius. But that's pretty easy. 15 minus 10 is just simply 5 degrees Celsius. And that's all the information that's given to us. And so we're given a change in time, which is what we need to solve for energy transfer, but we're not given the power. But if you look here, we have another formula for power. So we can write this out like this. We can say power equals Q divided by the change in time. But it's also equal to thermal conductivity, K, times the area of our thermal conductivity, or our wall, whatever's conducting heat, times the change in temperature, divided by the thickness, L. And we know all four of those numbers, so we can actually rewrite this to say, well, what is K? Well, K, we use pink, which is 0.10, and that's multiplied by A, which we said was just 2 meters squared, times the change in temperature, which we just said was 5 degrees Celsius, and then divided by L, which is just 0.04 meters. And so to figure this out, what we're going to do is we're going to plug this into our handy-dandy calculator. So I'm going to hit this button right here, this numerator over denominator button, and I'm just going to plug in my number. That's 0.1 times 2 times 5 on top, and then on bottom, I will just put 0.04 on bottom. And so what do we get for our power? We get power equals 25 watts, or we could write that as 25 joules per second. And so now that we know power, and we know the change in time here, and let me actually add that to this equation here. Let me move this over and say delta T, and we'll add that over here too. This is delta T. This is change in time. We can plug that in. We can say Q equals power times time. We just said power is 25 joules per second, or 25 watts, although I like joules per second for a very particular reason, multiplied by our change in time, which is 3,600 seconds. And hopefully that gives away why I like joules per second over watts, because seconds cancel out and we're left with Q equals joules, because of course energy is always measured in joules, right? And then to figure this out, all we're going to do is take 25 and we're going to multiply it by the time, which we just said is 3,600 seconds. And what do we get? We get energy transfer is 90,000 joules through this wall. And so what I want you to take away from this video is you can actually combine multiple equations to get your answer when you aren't given enough information for just one formula.